On 24th of September 2014, India became the first nation to insert a satellite into the Martian orbit within the very first attempt. It also became the first country in Asia to do so. So, how did India do this? Let's find out by going to Mars today. So Mars Orbiter Mission or MOM was India's mission to Mars undertaken by ISRO with the only goal of exploring Mars. So we just wanted to explore Mars and look out for life form, okay, or look out for evidences that will support life form in future. Or to be more specific about it, they just wanted to look out for methane gas, to detect methane gas, which is a good indicator for life form to begin with, okay. So now that we have discussed about the goals, let's briefly discuss about the spaceship designing. Okay, how was the probe that was sent to Mars, which is still orbiting in the Martian orbit, how was it built? What was it composed of? Okay, now we won't go into the very details of this topic. Let's discuss it on surface. Okay, so the MOM probe was majorly made up of two components. One is aluminium. Aluminium is known for its uses in aerospace engineering and also in aircrafts because it is light and its alloys are strong. Okay, so we have aluminium and we used a composed fiber of plastic, and that's a good waste management if you see, right? Now the bus or the model of the satellite was majorly based on Chandrayaan-1 with some slight modifications that will take us to Mars. Okay, and this satellite was launched using a PSLV rocket C-25, and that stands for, I guess, Polar Satellite Launch Vehicle. I got it right. Oopsie, I have to go. It's launch time. So MOM's journey to Mars began on 5th of November 2013 with the launch of PSLV at Satish Dhawan Space Center, Sriharikota. The launch went absolutely fine and as expected was soon followed by initial stage separations. Basically, initial stage separations is when a rocket goes like, she likes me, she does not, she likes me. And the MOM probe, the MOM satellite, which was sitting inside the rocket this whole time, was released into one of the Earth's orbit. Okay, but how do we confirm this? How do we know that the satellite, the MOM satellite, is in the Earth's orbit now? It is revolving around the Earth's orbit now. So in order to confirm this, we used the signals which were coming from the satellite and we detected those signals at different land locations on Earth. Now there is a small pothole in this idea if you see, because in the Pacific Ocean there is a huge gap. If you see Pacific Ocean, there is a huge gap between Pacific Ocean and the next piece of land. So in order to tackle this now, ISRO used a big brain move. They told two ships to take specific locations in the Pacific Ocean with their big antennas that will detect the signals from this MOM satellite. Okay, so a lot of space centers all around the world came together for this mission and I wish to thank them today. Okay, so also those two ships. Okay, and the results were confirmed. Okay, we were able to detect the signals at the different land locations and the ships also confirmed it, and we were sure that our satellite is in the Earth's orbit. Now according to one of my sources, I think the launch was planned on 28th of October 2013. Okay, but this launch was delayed due to the ships. Okay, the ships were not able to take the specific locations, maybe due to a storm in the Pacific Ocean. Okay, so the launch was delayed to 5th of November 2013. However, this mission was not at all delay friendly. Okay, because if you are going to learn it, okay, the launch of your MOM satellite follows a specific trajectory. Okay, that trajectory is very much unique and it's only followed for a few period in 780 days. Okay, so if we had to miss it on 5th of November, we had to wait till I think January 2016, and if we miss it again, we have to wait for 780 days more, but hopefully we didn't miss it. So now our MOM satellite is in the Earth's orbit, moving around it. Okay, we have to go to the Martian orbit now, so still we have to travel a lot. Okay, so this transition was in fact brought in by a series of steps, and let us go to through the steps now. Okay, so So here, for explaining purposes, I have drawn two orbits of Earth. Okay, our mom satellite is in the first orbit, the orbit which is closer to the Earth. That is the place where our PSLV rocket has left our mom satellite. Okay, it's over here. Okay, now every time our mom satellite reaches the perigee, we are going to do something interesting. Okay, first of all, what is perigee? Perigee is basically the closest distance of approach between the satellite and Earth. Okay, now you also know that these orbits are not perfect circles, right? They are ellipses. Okay, so there will be some disuniformity, right? Here the distance will be more, there the distance will be less, and at a point the distance will be minimum, right? And that point is nothing but perigee. So whenever a satellite reaches the perigee, which is the minimum distance of approach between your satellite and Earth, we are going to do this interesting thing. We are just going to put on the engine. Okay, we are going to fire on some fuel, right? Use some fuel, burn some fuel, and what will that do? That will impart some momentum to your satellite. Okay, so that will give some momentum. Your satellite will gain some speed. Okay, and it will start running away and will immediately put off the engine. Okay, and now what does that do? If you see, when we reach the perigee, we put on the engine, we burn some fuel. Okay, that gives our satellite some higher velocity, so it starts moving away. Okay, and we then put off the engine. Okay, so that will put our satellite in the higher orbit. It will just raise the velocity, and that velocity will be apt for the next orbit. Okay, so the raised velocity, due to its raised velocity, the satellite will try to move in a higher orbit now. Okay, and this is the resultant path of its higher velocity and the gravitational pull of the Earth. Okay, so now it's going to move in a higher orbit. Okay, so for explaining purposes, I have just shown one transition over here. Actually, we did a lot of them in this mission. We went up to the 6th orbit. Okay, so from the first orbit, following the same procedure, every time we reach the perigee, we are going to burn some fuel and we are going to increase the momentum, right? And that will move our satellite into the higher orbit, switch off the fuel, and that will our satellite will orbit in the higher orbit now. Okay, so yeah, so that was the procedure we followed every time from the first orbit to the 6th orbit. Okay, and yeah, some of you might ask the question that why only perigee? Why do we choose the perigee? The answer is very simple. It comes from Kepler's second law. A little bit of science over here. Yes, of course, that is what we are doing today. Yeah, so the Kepler's second law says that aerial velocity is constant. Okay, so suppose if we have these two areas over here, these two areas are covered in equal intervals of time. Suppose, okay, this area and this area are covered in equal intervals of time by our satellite. This area is swept and this area is swept in equal intervals of time. Suppose 2 hours. Okay, so these two areas by Kepler's second law will be equal. Okay, so you can see the consequence of this, right? Here the distance is large. Distance from the satellite to the Earth, right? From satellite to Earth is large. So it can move slowly, right? Whereas here you can see that the distance between the satellite and the Earth is less, which means that it has to move faster in order to make this area equal to this. So basically the idea that I want you to grasp is that the satellite will be faster when it's closer to the planet, right? The satellite will be faster when it's closer to the planet. That's a consequence of your Kepler's second law. Okay, so basically what is perigee? Perigee is the closest distance, right? So won't your satellite be the fastest over there? Right, it will be the fastest over there. Sorry for the fumble. Okay, so because if you see, I said the satellite will be faster when it's closer. So when it's closest, it will be the fastest, right? So at the perigee, we get a plus point over here. The advantage of firing our fuel at the perigee is that we have to use, it becomes energy efficient, right? Because our satellite is already in high velocity, right? It is at its maximum velocity, and you just give it an initial kick, okay, some kick in sort of the burning of fuel, okay, and just a small kick will move it into the higher orbit. So that's the advantage of doing it at the perigee, okay. So as I said, we followed this step for sixth orbit, till the sixth orbit, from the first orbit till the sixth orbit, and from the sixth orbit we again followed the step, okay, we again followed the same procedure. We burnt a lot of fuel at the perigee, okay, this time a lot of fuel at the perigee, and that made us escape the gravitational pull of the earth, okay. So our satellite was able to had gained so much of velocity called escape velocity, due to which it was able to escape the sphere of influence of our earth, okay. Sphere of influence is basically a sphere till where our gravitational field of earth is significant, okay. Beyond that, the field is not that much significant. You won't feel the pull beyond that region, okay. So by doing continuously following this process, we kept on increasing the velocity of our satellite, and finally we got so much of velocity termed escape velocity that we escaped the gravitational pull of earth, okay, and we were set free into the universe, and we were one step closer to Mars. So let me just explain you the final part of our journey over here. Here you can see that our mom satellite has escaped the gravitational pull of Earth, okay. So you can also note an amazing thing over here, that as the mom satellite is departing away from Earth, okay, the angle between Earth, Sun and Mars is 44 degrees, or I should say that the angle between Earth, Sun and Mars should be 44 degrees, okay. This is the orientation that I was speaking about. This is the pattern due to which we cannot afford delay, because we want at the time of departure the angle between Earth, Sun and Mars to be 44 degrees. It should be 44 degrees, and this pattern is followed for a short period, and it's followed every 780 days. That is why we could not afford delay, okay. So anyways, coming back, now we know that our mom satellite has escaped the gravitational pull of Earth, but it has not escaped the gravitational pull of Sun, right? Sun is more massive, so the gravitational pull of Sun is still acting on it. So we have the velocity of our mom satellite in this direction, but the gravitational force of Sun towards itself, right, towards its center, okay. So this is the effective path, as you can see over here, okay. This is the effective path of mom. This is basically a mom-son relationship. No more puns please, okay. So yeah, this is the trajectory that our mom satellite is going to follow, okay. So now before we get to Mars, I want to tell you one more thing, okay. So this was not the only method of going to Mars. We could have exploited the fact that the minimum distance between Earth and Mars is 54.6 million kilometers, right. We could have made a satellite that could have followed just that trajectory, right, burned down all the fuel and went in that path and slowed our satellite down when we reached Mars, and we could have got into the Mars orbit, right. But that would not be energy efficient, right. This project, if you see, is very much energy efficient. If you see, you burn fuel only when you want to raise the orbit, right. You burn fuel only when you want to escape the gravitational pull of Earth, okay. There is not a lot of fuel used in this process. This mission is in fact one of the cheapest. I may say it is the cheapest that the history has ever witnessed. Anyways, coming back, let's go to Mars. Okay, why am I delaying it? Okay, okay. So this mom satellite is going to follow this trajectory, and we can choose patience now, right? We can patiently wait for this, okay. But of course, the mom trajectory can get distracted, okay. It may get distracted. It's not perfect, right? We are not sure that it will follow the same trajectory, right. It may get distracted in between due to some explosions in space maybe, or due to some internal reasons also. Okay, so that time we had to just correct its trajectory. Okay, we can't just simply choose patience, so we have to make slight trajectory corrections in between, and we also have to slow it down when it reaches Mars, right? When it's about to reach Mars, we have to slow it down, because we know that if it has a very high speed, just like Earth gave up, right? Earth gave up when its speed exceeded the escape velocity, Mars will also give up. It will say, I'm not holding you in my orbit. So in order that your mom satellite that your mom satellite is accepted by Mars, it should be at some decent velocity, right? So when we are about to reach the Mars, we will slow down its velocity. That is the next thing that we do besides correcting trajectory in this whole period of 298 days, I guess. And on 24th of September 2014, our Mars orbiter mission was successful. Our mom satellite entered into the orbits of Mars and it was welcomed. Okay, a mission that had chances of less than 30% of succeeded within the very first attempt. So if I had to highlight something about this mission, I will surely highlight how cheap it is and how energy efficient it is. If you see, the total mission cost was 74 million US dollars, which is 454 crores in rupees. The distance traveled is 650 million kilometers, and if you find cost per kilometer, that is just 10 cents, okay, or you can say 7 rupees per kilometer. To put that in perspective, a taxi ride in Ahmedabad costs around 10 rupees per kilometer. We went to Mars, it just took us 7 rupees per kilometer.